Well, hello everyone. My name's Paul Shah and I work at the University College in London, and I'm also part of the Dark Energy Survey Supernova Working Group. So what I'm here to talk to you about today is Evolving Dark Energy or Supernova Systematics, which is a title I've borrowed shamelessly from George Estaffiu's paper of the same name, and we'll come back to that in just a minute. Okay, so the outline of this talk today, we're briefly going to review some of the existing results from the DES and DESI collaborations and why supernova matter to those results. We're going to look at how the sausage is made, which is how the supernova observations are turned into distances. And we're going to answer the question of evolving dark energy or supernova systematics, at least as far as we're able to. Okay, so just a quick look at the background probes that we're going to be using. Supernovae, of course, are empirical standard candles, and the rulers that we use are baryon acoustic oscillations and the cosmic microwave background. And lastly, we use a little bit of information from inhomogeneities via CMB lensing. Now, in this talk, we're going to be discussing results in the context of a so-called CPL parameterization of the evolving equation of state of dark energy, which is WA. And WA is the key parameter here, which tells you whether dark energy is evolving or not. So let's have a look at DES 5-year and the Hubble diagram. So we have distances here on the y-axis and redshift on the x-axis. Now the dark energy supernovae are the blue dots here, which you can see mostly high Z observations, and we supplement those with low Z to build a Hubble diagram all the way out from redshift 0.03 to redshift 1. Now, when we put that data together with results from the CMB and SDSS BAO, we obtain the following solution, which, as you can see, has a WA parameter which is different from 0. And the degree to which it's different from Planck lambda CDM is quantified by 2.8 sigma. Now that result doesn't change particularly much if we switch from SDSS to the more modern Dark Energy Survey, BAO. In fact, the level of significance increases slightly to be 3.0 sigma discrepant to lambda CDM. Now, moving on to DESI, which, as many of you will know, released its data release 2 this year. Now, if we just look at those BAO, which are here as the dark grey points in the upper panels, and we add the CMB data to that, but we do not yet include any supernova data, we can see, because the horizontal black line corresponds to the Planck lambda CDM solution, we can see that the data points are not particularly consistent with Planck. In fact, within the lambda CDM model, we can say that we are discrepant by 3.1 sigma without including any supernova at all. However, we cannot say for sure if this is evolving dark energy or perhaps a modest spatial curvature corresponding to an open universe. And this point was made by Chen in their 2025 paper. So we could say that we don't favor lambda CDM, but we're not sure if it's evolving dark energy or not. Now let's look at the supernova, and here it's the DES 5-year sample. So in particular, I want to draw your attention to the red dashed and the green dashed lines, which correspond to the evolving dark energy solution. Now, particularly the difference between the mid-Z and the low-Z supernova, you can see by eye is driving some of the preference in the bottom panel there. The open squares correspond to the average of the supernova distances in bins. In particular, we can see that for the baryon acoustic oscillations, we have an upward trend with redshift of moving from BA over to closer than Planck lambda CDM. Whereas for the supernova, the trend is opposite. As you go to low Z, you have supernovae that are further than Planck lambda CDM. And when you put those two together, the significance for lambda CDM is decisive at a level of over 4.2 sigma. And just to add that the DESI BAO are consistent with DES BAO. Now, when we change the supernova sample to Pantheon, the significance is much less, and it's easy to see why in the bottom graph. The difference between the high Z and the low Z supernovae is now much reduced compared to Planck lambda CDM, and therefore the significance of that dataset is only 2.8 sigma divergent with Planck lambda CDM, which is more or less the same significance as we would have attained with SDSS BAO, CMB, and the DES 5-year sample. Now, just a little bit of a word about whether we should consider Pantheon or DES as our go-to sample. Now, you might think, okay, Pantheon has spectroscopic classification and similar numbers to dark energy survey, so why not use that? However, Pantheon contains some very old photometry, going back to 1980 in one instance. And also, Pantheon combines 20 different surveys, all with different filter characteristics, different telescope platforms, which all need to be cross-calibrated. In contrast, DES uses only DES data for high Z, and low Z is mostly just a foundation sample with a little bit of CFA and CSP. Also, the light curve filters have been updated comprehensively from 2010 vintage to 2023 vintage for DES. So overall, I think you should prefer DES rather than Pantheon. Okay, let's take a look at how observations of supernovae are converted into distances. So on the right-hand side here, you can see the observations in broadband filters GRI and Z from an early release of DES data arranged as a time series. So you can see the peak brightness and then the typical decline of the type 1a supernovae after peak brightness. Now, these observations are fitted to templates, which you can see as the solid lines. And from those template fittings, we obtain the magnitude of a supernovae, which roughly corresponds to a peak magnitude in the B band, the color, and something called the stretch, which relates to the duration of the explosion. Now, bluer and longer lasting explosions are brighter than otherwise. Now, once we determine that fit, we can also use it to calculate the probability that what we're looking at is a genuine type 1a supernovae and not any other type, for example, a core collapse supernovae. And that determination is very robust and uses a number of different ways, such as machine learning and otherwise, to determine the probability of the type 1a. Now, after the supernova has faded, we obtain the host galaxy redshift by pointing a spectroscope at the source galaxy. Now, the last stage in the process is to fit this for regression parameters, which minimize the scatter around the Hubble diagram, and also to make a couple of adjustments for bias. Now, that's very important. I'll come back to that in a minute. And environment. The environmental factor relates to the fact that supernovae brightnesses are slightly different depending on the properties of the host galaxy, and that's still very much the subject of active research. So the final distances that you can download from our server are the distance modulus, which is the combination of all of these observations and the environmental and bias factors. Now, there's one very last important point here, which is you can see the supernova absolute magnitude is included at the end of that formula. Now, that absolute magnitude is degenerate with the Hubble constant, which is to say that when we determine the distances, we are assuming a particular Hubble constant and we are assuming a particular absolute magnitude of a supernovae. Now, the data itself tells you neither of these. Because we do not know the absolute magnitude of a supernovae, we only know the relative brightnesses. We do not know the Hubble constant. Of course, for convenience, we publish the data in this way. However, if you wish to know the Hubble constant from using supernova data, you will have to calibrate the supernovae, and that means obtaining distances to them in an absolute basis. Now we can do that either using other standard candles in the nearby universe, such as Cepheids, or we can calibrate supernova using the angular diameter distances that we see in the CMB. The other thing we can do, of course, is to treat m as an unknown variable and marginalize over it. Now let's come on to the main part of this talk, which is evolving dark energy or supernova systematics. So George Estafio wrote a paper where he compared the dark energy survey and the Pantheon Plus samples and raised questions about the strength of the evidence for evolving dark energy. So let's look at what George did. Now the same supernovae happened to be in both samples. Now, the reason for that is that an earlier release of DES data, the 3-year sample, was released in time to be included in the Pantheon Plus sample. Also, Pantheon Plus and DES used low Z data in common. Now, what George did is to compare the same supernovae that are in both samples, and let's see how their differences are different. So on the y-axis here, we see the difference between the Pantheon distances and the distances in DES. And in particular for the foundation sample, which is 118 supernovae in common, you can see that the differences between Pantheon and DES are of the order of 0.05 magnitudes. Now, this is very important for the preference for evolving dark energy because remember, that was driven by the difference between the high Z and the low Z samples in DES. Now, do please remember that because DES is an uncalibrated sample, it's not specifically foundation. It is really the tilt in the Hubble diagram that matters. So we can't locate it to foundation or to DES. All we can say is that the supernova Hubble diagram is tilted for the same supernovae between DES and Pantheon. Now, what on earth is going on if the same supernovae have different distances? How can this happen? Well, we've published a paper from the Dark Energy Survey that explains this. And it's basically down to the selection function differences between the two samples. Now, what is selection here? You have to remember that supernova surveys are magnitude limited. So when we come to look at a scatter of observations, let's say in a particular given redshift bucket, we are generally observing only the brighter portion of the sample. And this is illustrated in the panel up on the left-hand side here. Because we're only observing the brighter portion of a sample, when we come to average our observations, they will be brighter than the true mean of a sample. Now we can calculate that difference through simulations, and what we do is the bias correction adjusts all of the supernovae in that particular bin so that the observed mean matches the true mean, and this is what the bias correction does. That bias correction is of course a function of the width of the scatter of a distribution, and also the particular selection function, specifically the limiting magnitude of a survey and other factors. So how does this matter to Pantheon and to DES? Well, specifically, the DES subsample that was included in Pantheon was brighter and bluer than the full sample that was included in DES. And you can see the difference here in the lower panel, which are the orange dots, the DES 3-year sample, versus the full 5-year sample, the blue dots. Now, the scatter models were also changed a little bit between DES and Pantheon, but not by much. And remember, if the bias model changes, then the distances change. So let's look and see how this makes a difference to distances. From a distance of roughly about difference of about 0.04 magnitudes between high Z and low Z, we can attribute 60% of that difference to changes in the bias correction, which are expected and explained by the different selection functions of a survey and the slight update to the scatter model. Now, there was a small change as well due to changes in the supernova host galaxy mass measurements, which have a little bit of influence on the environmental correction. And then there's a small amount that is unexplained, but it's probably down to some model updates, such as the salt-free light curve fitter template updates. Now, there might still be some reasons to be cautious. Looking at the history of supernova observations, of course, scatter models have evolved, and particularly for the 2010 vintages, there was about 0.04 magnitudes difference between those two models, which was in the Pantheon sample and was included as a systematic there. However, those 2010 models are not a good fit to modern data, and a new model was proposed by Brout and Skolnick in 2021, which attributes the majority of supernova intrinsic scatter to host galaxy dust extinction. That is how the light of a supernova makes its way out of its host galaxy to the top of that galaxy. Now, that does improve the fit to the data, but also resulted in a change of about 0.04 magnitudes between low Z and high Z from the old 2010 vintage models. Now, in Pantheon Plus, those old models were included as systematics, but in a DESI 5-year sample, we just changed the model parameters of a BS21 model and include those as systematics. So the conclusion is there have been historical scatter model updates which have produced changes to distances which would be material to the cosmology. However, those changes were consistent with the published systematics at the time. So in conclusion, the differences that were observed between the Pantheon Plus and the DES samples for the same supernovae are expected and due to the different selection functions. I would argue that DES is a better sample to use than Pantheon Plus. There are less surveys that are used in DES, better characterization of the instruments and the selection functions. Now, if you don't like bias corrections, there are alternatives. But for example, union-free, which uses Bayesian methodologies, does produce results that are consistent with DES 5-year. Now, obviously, scatter balls have changed throughout history. Have we got the last word? Well, probably not. And it's very interesting to learn from the new survey data that's coming out. Of course, Zwicky Transient Facility has published new data, and we're very much looking forward to data from the DBAS survey and Rubin LSST to learn more about the intrinsic scatter of supernovae. And that concludes my talk. Thank you very much for listening.